Now I want to spend some time talking about what it means to shift to equilibrium. We know reactions will reach equilibrium. What does it mean when they shift to reach that ultimate and inevitable equilibrium? So the idea of shifting to equilibrium comes from the fact that we never mix we don't create equilibrium mixtures just natively in the lab when we mix chemicals together. You throw some chemicals in a beaker in a reaction vessel, they're going to be at random ratios, right? There's only one equilibrium ratio, and there's infinitely many possible ratios. So it's very unlikely that you will ever prepare a mixture that's perfectly at equilibrium. And so what will happen is when you mix your reactants, products, whatever it is together, chemical reactions will occur. They will change. The relative amounts of each reactant and product that are present in your mixture will either increase or decrease. And we use language to describe these relative shifts. So you mix some reactants and products together, they change, they react, and then the shift can either be towards products, which we also call to the right because we write products on the right side of a chemical equation, or the reaction can shift towards reactants or to the left because reactants show up on the left side of a reaction equation. So these relative amounts are going to change. Do the relative amounts change in such a way that the reaction shifts towards products or towards reactants? So let's look at some examples. If we have a reaction at equilibrium, for example, 2SO2, that's these molecules, plus O2, that's these molecules, produces 2SO3, the big molecules. And this reaction is defined by an equilibrium constant, Kc. So if we're at equilibrium, that Kc, that ratio determines the relative amounts. I have some reactants, I have some products, I have them all mixed together. And we know that the reaction is still occurring. It's not stopped at equilibrium. So we make some products, maybe some other products turn back into reactants. And we're going back and forth in this way. There's this dynamic equilibrium. Well, we don't usually start at equilibrium. Usually we start with, say, only reactants, right? So I have, again, my SO3s and my O2s, but there's no SO3 molecules present in this mixture. I only have reactants. So what are they going to do? They're going to react. We know that molecules don't stop reacting when they reach equilibrium. The reactions are just going to occur. SO2 will react with O2, but the SO3s might go backwards, might unreact or go back into the reactants. But there's no product here to react, so we will inevitably, the only thing that can happen is make some product. So product molecules will start to occur, and this is just going to keep happening. We slowly make more and more product molecules. The SO3 amounts start to increase. And this increase in SO3 will continue until equilibrium is reached. And that equilibrium will be defined by Kc. We started with only reactants, but we end up at the same equilibrium ratios that were defined by Kc, right? This slide shows the same mixture of what I started out initially. If you don't remember the perfect placement of everything, but there's those relative ratios of the reactant molecules, the SO2 and the O2, and the SO3. Those relative ratios are always defined by Kc. In this case, we started with only reactants. We have now made additional SO3 molecules in the process of, quote, shifting to equilibrium. The relative amounts of everything changed in such a way that we have more SO3 molecules than when we started, but it's still the same equilibrium. That shift depends on where you start and where the equilibrium is. We could also set up in the kind of opposite extreme. We start with only product. I only have SO3 molecules now. So the opposite is going to happen. We know those SO3 molecules can react to become the SO2 and the O2. That's the only thing that can happen here. The reaction's just, if it can occur, it will. So we make some, quote, reactant molecules, some SO2 and some O2. And this is just going to keep going. And this will continue to happen. The SO3s will react, more and more of the O2 and SO2 will become present. There was none initially, so the amount will increase. And it only stops when equilibrium is reached. It's all about reaching equilibrium. The equilibrium here looks the same as the other equilibriums because I have not changed what the chemical reaction is, so the value of Kc is always the same. The value of Kc here has not changed and will not change. And so we have, that's just kind of the situation that we're in. The equilibrium constant defines what the equilibrium mixture will look like. The shifts to get there can be different because we can choose different starting points. Do we have more reactants or more products? In this case, we made a lot more SO2 and O2 because we didn't start with any of it and we lost SO3. So these graphs show the same chemistry, just kind of overall, instead of on a molecular basis, kind of one at a time. Once you define a chemical reaction, equilibrium is always going to look the same, right? This equilibrium is always going to be exactly the same. The difference, the possible differences in how these things can change, or the difference of kind of language comes from this idea of the different shifts, because the shift depends not only on the equilibrium where the reaction ends, but also where the mixture started. So if you start with only this, these would be the reactant molecules, SO3 or SO2 and O2, the first example, those amounts will decrease and we will get more SO3. Conversely, if we start with a different set of initial conditions, the shift will be different. The equilibrium is the same, but the relative change appears different. This would matter if we wanted SO3, right? If say you thought you only had SO3, the fact that it shifts back to reactants is no good. If you have no SO3 and you want some, shifting to products is great because all of a sudden you have some SO3. Again, whenever we talk about a shift to products, what that means is that the reactant amounts decrease over time and product amounts increase. Those reactant molecules are becoming products. The relative amounts of everything in my reaction mixture is changing in such a way to favor the creation of products. So that's really all that's shifting. The reaction just happens. The molecules react like they're going to anyway. But with the relative amounts, I get more products than I started with at the expense of the reactants. Shift to reactants is therefore the opposite. You have, some amount of product initially that decreases and is compensated by a creation in the amount of what we call reactants. So it's all about the initial condition. This is the exact same chemical reaction, the exact same equilibrium, but I had different starting conditions. So the apparent shift, what I've lost or gained, is different. How different is that from what the inevitable will be? If you mixed perfectly at equilibrium, you would get no shift, but that's never going to happen. So kind of put some, if we kind of think about an example, lead 2 chloride is not, it can dissolve. We can write an equation for it, Pb2 plus 2 chloride. We can come up with an equilibrium constant for this, the two things that are dissolved, and it's less than 1. So this is a reactant favored equilibrium, right? The Kc is much less than 1. So we know that if you took solid lead 2 chloride and you put it in water, it would not tend to dissolve. We also would, kind of common language say it is insoluble. So not much will dissolve. If you have your solid lead 2 chloride, this is a photo of what it looks like. Not much is going to change. But if you put some into water, some will dissolve, right? Because you can use the equilibrium constant to figure out what those concentrations are supposed to be at equilibrium. If you just put solid lead chloride into water, there are no dissolved ions into it. And so you're not at equilibrium. You need to make some product. So this is a very reactant favored equilibrium, but because of how you set it up, you put this stuff into water, it needs to shift to products. Some will dissolve in order to produce those ions that should be present at equilibrium. You do need some of these product ions to be there. So the shift to products has to occur. It's not a big shift to products because the overall equilibrium is reactant favored, but there is still a shift towards products. After you reach equilibrium, more product ions are present than initially, which was 0. So you had to have a shift to that side. There we go. Another one down. Participation 215 is what we're looking for. Making good progress. Just got a few more videos. See you in the next one.